3 Atlas has created an unprecedented predicament for NASA, the preeminent space exploration organization on Earth, plunging it into a crisis that is escalating beyond its capacity to manage. Every available telescope is focused on this phenomenon. Every global government is keenly observing. Yet NASA has retreated into a shroud of silence. The pertinent data is accessible. The visual evidence exists, but entry is strictly barred by a phrase that, at first glance, appears innocuous. NASA News Lockdown. It sounds harmless until one grasps its true implication: a complete information blackout. Consequently, NASA now stands precariously on the brink of a revelation that could lead to its undoing. To speak out risks triggering widespread global unrest. To remain silent would be to tacitly endorse every fear that has been deliberately suppressed. This is because 3 Atlas is not merely challenging the established laws of physics. It is actively dismantling the very notion of controlled reality. Remain with me until the conclusion. For tonight you will come to understand that the unspoken truths NASA holds about 3 Atlas possess the potential to fundamentally alter our perception of the cosmos and our place within it. If this narrative prompts you to question the unfolding events in the heavens, do not miss what is to come. Please engage with a like, subscribe to our channel, and leave a comment indicating your location, the current time there, and whether you believe we are being presented with the complete truth. Furthermore, if you wish to contribute to the expansion of this community, kindly share this video on X, Facebook, Reddit, or even within your personal group chats. Your support is the driving force that enables us to continue uncovering stories of this magnitude. Therefore, thank you for standing by us. Part 1. Cold Open. NASA possesses the photographic evidence. The orbiting satellites have indeed observed it. Yet 2 weeks later, there is only silence. You are familiar with that sensation when you encounter something that defies explanation, something that sends shivers down your spine. Now envision yourself as part of NASA, commanding the most sophisticated telescopes ever engineered by humankind, all trained on an entity that, by all accounts, should not exist in its current form. You hold the data, you possess the images, and yet you are prohibited from uttering a single word. This is the unfolding saga of 3 Atlas, an interstellar comet that did not simply pay a brief visit. It has forced the world's most influential space agency into an impossible decision. Allow me to vividly illustrate the situation. It is July of the year 2025. Headlines begin to proliferate across all media platforms. Interstellar Comet 3 Atlas. Scientists convene at academic symposiums. Images captured by telescopes are circulated as if they were collectible items. Astronomers engage in their characteristic behavior when experiencing excitement, while simultaneously striving to maintain a veneer of professionalism. They carefully articulate their findings into microphones, hedging every declaration with qualifiers such as "preliminary data suggests" and "further observation is required." However, if one scrutinizes the detailed logs of the collected data, examining the timestamps on the observation records, a peculiar anomaly begins to surface. There are discernible gaps, interrupted sequences, periods where continuous monitoring would be anticipated, yet instead, there is a complete absence of information. This signifies a radio silence from the very agency entrusted with serving as humanity's eyes in the vast expanse of space. Allow me to present a claim, and I urge you to contemplate it for a moment. 3 Atlas has not merely challenged the principles of astrophysics. It has maneuvered NASA into a precarious position where every conceivable action carries a significant risk of catastrophic consequences. Consider it from this perspective. If they were to disclose too much of what they have witnessed, what would be the inevitable outcome? Widespread panic. The emergence of conspiracy theories that would render the skepticism surrounding the moon landing seemingly rational. Social media platforms would erupt. Cable news channels would broadcast 24 hours a day, 7 days a week, featuring increasingly breathless speculation. The lines of communication to congressional offices would be overwhelmed. Every fringe theory would be amplified to the point where the original signal would be utterly lost in the cacophony of noise. Conversely, if they maintain their silence, if they continue to postpone the release of information, if they persist in stating that the data is undergoing review, if they permit weeks to elapse while the entire world watches and waits with bated breath, their credibility will inevitably erode. That invaluable trust, meticulously built over decades, will begin to crumble. Individuals will start to pose the single question that instills profound dread in every scientific institution. What are they concealing? And this is where the situation becomes truly compelling. This scenario is not unfolding in a vacuum. The political timing is a crucial factor. NASA's budgetary cycles are indifferent to the arrival of celestial visitors. Congressional oversight hearings are scheduled months in advance. Budgetary reviews proceed regardless of whether an interstellar object decides to exhibit unprecedented behavior. The intricate bureaucratic machinery of a vast federal agency does not cease its operations simply because the universe has presented an unexpected challenge. Then there are the established protocols. The protocols. NASA operates under a framework they term NASA-wide news protocols. When a situation is designated with this label, it necessitates approval not only from a single department, but from a comprehensive chain of endorsements, clearances, legal assessments, and strategic communication plans. The entire system must meticulously follow its prescribed process. And this system operates at the deliberate pace of bureaucracy, not at the velocity of a comet hurtling through our solar system. The public anticipates answers. We have grown accustomed to immediate gratification, have we not? We expect that when an event occurs in space, NASA will promptly disseminate information through tweets. They will release the accompanying images. They will conduct press conferences. We have been conditioned to anticipate a high degree of transparency, delivered instantly and comprehensively. Therefore, when that customary transparency abruptly vanishes, when the usual channels of information flow simply cease, people take notice and begin to ponder the reasons. But here is the element that should truly capture your attention. What if the observations made by NASA were not merely unusual? What if it was something far beyond a mere comet? What if their telescopes captured an entity that defies categorization within the established frameworks we have devised for celestial bodies? I want you to truly grasp the gravity of this question because somewhere within a facility in Houston, Pasadena, or Washington, an individual is grappling with precisely this dilemma. They have witnessed the images. They comprehend the implications of the data, and they must make a determination regarding the dissemination of information that could fundamentally alter humanity's understanding of its cosmic context. This concern extends beyond the mere apprehension of the unknown. It also encompasses the profound influence of secrecy and the consequences that arise when those entrusted with imparting truth find themselves incapable of doing so without precipitating widespread chaos. It represents a collision between scientific accountability and the imperative for institutional preservation. If you seek the authentic narrative, it is not to be found in the official press releases. It is not contained within the carefully crafted statements issued by NASA's Public Affairs Division. The genuine story lies in what they are deliberately withholding from public view. It resides in the images that have not yet been released, in the data that remains in processing queues, and in the private discussions occurring behind closed doors, where individuals are endeavoring to formulate an explanation for the inexplicable that will not incite a public outcry. Every space agency possesses established procedures for handling unexpected discoveries. They have flowcharts, decision trees, and hierarchical command structures. However, these procedures were originally conceived for a reality where anomalies adhere to predictable classifications. This might include equipment malfunctions, the detection of an unforeseen asteroid, or the observation of an intriguing yet explicable phenomenon. These protocols were not designed for something that so thoroughly deviates from established norms that one cannot even definitively assign it to a recognized category. And so we find ourselves in this predicament. NASA possesses the corroborating evidence. The entire world is observing the situation. Time is of the essence, and with each passing day that elapses without a complete disclosure, the underlying tension intensifies incrementally. What transpires when the institution responsible for unveiling the marvels of the cosmos becomes the very entity suspected of concealing them? What they are not revealing to you, that is the true story, and we are about to delve into the precise details of this obscured timeline. Part 2. What the public does not see. Let us revisit the genesis of this event. In July of 2025, the ATLAS survey, which stands for the Asteroid Terrestrial Impact Last Alert System, detected an anomaly within its automated scanning processes. It registered as a transient object, a term in astronomical parlance signifying something that was not previously present and is unlikely to remain for an extended period. Initially, it was merely a faint signal, a single data point among thousands that the survey catalogs on a monthly basis. However, this particular detection was distinct. Within a span of 48 hours, it became apparent that the object's trajectory was anomalous. It did not exhibit the motion characteristic of objects native to our solar system. Its orbital parameters were entirely unconventional. It was traveling at an excessive velocity. Most critically, it was following a hyperbolic trajectory, a technical descriptor, indicating that it originated from beyond our solar system. It was interstellar. It is important to note that interstellar objects are not entirely without precedent. We have encountered visitors from beyond our solar system in the past, but they are sufficiently rare that their detection commands the immediate attention of the entire astronomical community. Consequently, the information was disseminated. The Gemini Observatory was directed to focus its powerful telescopes on the object. Hubble Space Telescope was allocated observation time. The European Space Agency's ExoMars mission possesses an instrument designated as the Cassis camera, which was reoriented to acquire imagery. Within a single week, some of humanity's most advanced observational instruments were collectively trained on this singular entity. And it is at this juncture that the situation becomes truly intriguing. If one were to meticulously track the dates of public data releases, mapping out precisely who published what and when. A discernible pattern would begin to emerge, or rather, the absence of a pattern where one would logically be expected would become apparent. The European Southern Observatory, ESO, unveiled its initial images on the 23rd of July. The Gemini Observatory followed suit, publishing its data 2 days later. However, NASA, the agency operating the largest fleet of space telescopes, the agency poised to lead such a significant discovery, remained silent. Its rendition of the captured images did not appear in the public archive. Not yet, at least. Days bled into weeks. References began surfacing in scientific publications to preliminary observations and data currently undergoing review. This ubiquitous phrase, "under review," started appearing with increasing frequency. For those familiar with NASA's operational procedures and its internal organizational structure, this designation signifies a critical development. The object has been flagged for special handling. Now, regarding this designation known as NASA-wide news, it is not a term typically found in public press releases, nor is it formally defined in any publicly accessible document that I have been able to locate. However, it appears in internal communications and is documented in inter-office memos. From piecing together accounts from individuals who have worked within the system, it is understood to be a classification indicating that this is not merely an issue pertaining to a single mission. Rather, it is a matter requiring coordinated action across the entirety of the agency. The question of who initiates this specific designation is where the complexity truly lies. It could originate from the Communications Office, which bears the responsibility for ensuring NASA's public messaging remains consistent and does not inadvertently create complications. It could stem from the legal review team, tasked with ensuring that the release of certain types of data does not contravene any existing regulations or international treaties. Alternatively, it might originate from mission management, who may identify data that raises significant concerns, necessitating oversight from higher levels before public dissemination. Allow me to provide a concrete illustration of how this process unfolds. The European Space Agency, ESA, releases an image of 3 Atlas, revealing unusual features within its coma, the gaseous envelope surrounding the comet's nucleus. This image is publicly accessible. Anyone can download it. Yet, NASA's equivalent observations, collected around the same temporal period, remain in its internal processing queue, are still under review, and have not yet been cleared for release. The pertinent question then becomes, why? What could possibly be contained within those images that necessitates such a stringent level of scrutiny? Let us explore the potential explanations. It is conceivable that the object is exhibiting emission spikes, a phenomenon where comets release gas when exposed to the sun's proximity. This is a well-understood behavior. However, what if these emissions are occurring at an unexpected time or from an uncharacteristic location? What if the fluctuations in brightness do not align with the expected physical processes? Alternatively, the anomaly might pertain to its trajectory. Gravitational physics is an extraordinarily precise field of study, enabling us to predict the motion of celestial bodies with remarkable accuracy. What then occurs when an object deviates slightly from its predicted path? When subtle variations are observed, minute enough to be potentially attributed to measurement error, yet persistent enough to continually appear in the data? Or perhaps, and this is where the situation becomes particularly intriguing, there may be structural characteristics that appear unconventional. Anomalies in brightness might suggest that the object does not possess uniform reflectivity. Patterns observed in the imaging data could be interpreted as bearing a resemblance to non-natural formations. Imagine yourself as the scientist who first makes such a discovery. You are seated at your workstation, performing routine analysis on what you anticipated would be a standard observation of an interstellar comet, when something within the data compels you to pause. It prompts you to rerun the analysis and to summon a colleague, exclaiming, "Look at this. Tell me I am mistaken." Naturally, you would flag it. And that flag initiates a review process. The review board examines the findings. They may express concern, or they may be skeptical. Regardless, they render a decision. This data enters the internal review queue rather than the public archive. This is not necessarily indicative of an intent to conceal information, but rather a necessary step to allow for a thorough understanding of what is being observed before it is presented to the world. Consequently, the data remains in the processing queue, while the public receives press releases detailing ongoing observations and preliminary findings, and while agencies like ESA continue to publish their respective data. The disparity between what has been observed and what has been officially released continues to widen. In the current era of social media, secrets derive their power from the very absence of information. Each day that NASA withholds data contributes another data point for those attempting to decipher the unfolding situation. The silence itself conveys a profound message. Part 3. The anomaly itself. So, what precisely is 3 Atlas? Let us begin with the established facts. It is currently on a hyperbolic trajectory, indicating that it originated from interstellar space and is destined to return to interstellar space. It is not gravitationally bound to our Sun. This is a transient visitor, a cosmic traveler passing through our celestial neighborhood. The object was initially detected at a distance of approximately 4 astronomical units from the Sun, which is equivalent to 4 times the distance between Earth and the Sun, placing it roughly within the orbital path of Jupiter. As it approaches its perihelion, the point closest to the Sun, it begins to exhibit characteristics typical of a comet, including outgassing and the development of a coma and potentially a tail. Up to this point, these behaviors appear quite normal, do they not? An interstellar comet, behaving as expected. However, it is at this juncture that the conventional observations cease, and the unusual phenomena begin to emerge. The jets. Comets generate jets. When volatile substances on their surface are heated and explosively expel into space. These jets are well understood phenomena. They should predominantly point away from the Sun, driven by solar radiation pressure, and the solar heating of the Sun-facing side. Yet, the jets emanating from 3 Atlas do not conform to this expected behavior. Technical papers and observation logs contain reports of activity that appears to be directed towards the Sun rather than away from it. This is an occurrence that should not happen, akin to observing water flowing uphill. One can certainly devise explanations. For instance, perhaps rotational dynamics are involved, or the object is tumbling in a specific orientation that produces this effect. It is also possible that subsurface voids are channeling gas in unforeseen directions. However, none of these explanations perfectly align with the observed data. Then there is the matter of its luminosity. Comets typically brighten as they approach the Sun, a predictable phenomenon. Yet, 3 Atlas displays luminosity fluctuations that do not correlate with the smooth, predictable curve one would anticipate. There are sudden increases and decreases, variations occurring too rapidly to be attributed solely to changes in distance or the angle of illumination. Some researchers have proposed the theory of fragmentation, suggesting that the object might be breaking apart, which would lead to abrupt changes in brightness as new surface areas are exposed. This is a plausible hypothesis. However, if fragmentation is occurring, where is the debris? Where is the field of fragments that one would expect to trail behind it? Let us draw a comparison to Oumuamua, the first confirmed interstellar visitor, detected in October of 2017. That object presented its own unique set of peculiarities. It exhibited non-gravitational acceleration, meaning its velocity changed in ways that could not be solely explained by the sun's gravitational influence. However, it did not display any outgassing, nor did it possess a coma or a tail. It was accelerating without any visible means of propulsion. The scientific community proposed various explanations, such as the venting of gas, in a manner undetectable by our instruments, or its configuration being akin to a flattened disk or a solar sail, which would allow solar radiation pressure to exert influence. While these explanations were largely functional, they necessitated the stretching of certain assumptions. With 3 Atlas, we are venturing into entirely different territory. This object is exhibiting behaviors that are extraordinary, even by the standards of phenomena that are already considered highly unusual. Some scientists have described its features as not entirely conforming to existing models. This is a diplomatic phrasing, implying that we are unable to fully account for our observations. There are reports indicating asymmetric patterns of illumination. Instead of the nucleus being the brightest point, with the surrounding coma uniformly diminishing in intensity outward, there are indications of internal structure, regions that are brighter than expected, and halos that appear in front of the nucleus, rather than behind it. Allow me to emphasize a crucial point. Telescope imagery is complex. It is not akin to a straightforward photograph. It represents processed data, meticulously calibrated and corrected for various instrumental effects. Occasionally, what appears to be structural detail may actually be an artifact of the image processing methodology. Cosmic rays striking the detector can generate spurious signals. Atmospheric distortions can create phantom features. However, when multiple instruments aboard numerous telescopes consistently reveal similar anomalies, it becomes imperative to take these observations seriously. It is at this point that one must consider the genuine possibility that what is being observed is indeed real. There is one particular observation that is repeatedly mentioned in the technical literature, albeit with carefully qualified language. An analysis of the debris field, or what should constitute the debris field, reveals geometric patterns. These are not the random distributions one would anticipate from a fragmenting comet, but rather something more organized and regular. Is it artificial? This is the question that no one is eager to pose openly, because the moment one begins to entertain the possibility of artificial construction, the realm of inquiry shifts from astronomy to a domain fraught with profound implications. It is akin to opening a door that proves exceedingly difficult to close. Let me illustrate how this manifests within the data. Imagine observing luminosity measurements plotted over time. Standard cometary behavior would typically demonstrate a relatively smooth increase in brightness as the object approaches the sun, perhaps with some random fluctuations due to sudden outbursts. However, what if, instead, you observe periodicity? What if the fluctuations in brightness recur at regular intervals? What if, upon performing a Fourier analysis, you identify frequencies that do not correspond to rotational periods or any other known natural phenomenon? I must be unequivocally clear, this is not definitive proof of anything. Periodic signals can arise from a multitude of natural processes. However, it is precisely the kind of observation that warrants closer examination and triggers internal alerts. NASA has observed something. The orbiting satellites have captured it. The fundamental question is whether what they have witnessed can be explained by the established laws of physics, or if it necessitates the consideration of possibilities that are, to put it mildly, disconcerting. This is not merely an interesting cosmic oddity. This is a phenomenon that does not readily fit within our established framework of understanding. And for an organization whose very foundation rests upon being the authoritative source of information regarding extraterrestrial phenomena, encountering something that defies this established framework presents a significant challenge. Did NASA detect movement? Not simply drift or trajectory, but movement indicative of deliberate control? Did they witness something that triggered an internal alarm of sufficient magnitude to warrant the complete lockdown of the data pipeline? We do not possess definitive answers. However, the very fact that these questions are being raised weeks after the initial observations strongly suggests the considerable gravity with which this situation is being regarded. Part 4. The bureaucratic lockdown. NASA is not a monolithic entity. It is tempting to perceive it as a singular, unified organization, but in reality it is an extensive network comprising numerous centers, diverse missions, private contractors, and collaborating organizations. While they all operate under the same overarching mandate, they possess distinct priorities, operate on differing timelines, and report to various levels of management. When an object like 3I Atlas is observed, the resulting data does not converge in a single location. It is disseminated across multiple departments. Mission operations teams process the raw data. Science leads conduct in-depth analyses. Communications departments prepare public messaging strategies. Furthermore, there are liaison offices, legal review departments, export control divisions, and the Planetary Defense Coordination Team. Each of these offices has a vested interest in what information is released and when. The designation NASA-wide news appears to be a bureaucratic marker intended to initiate a comprehensive review process involving multiple departments. Even if a matter isn't officially classified or doesn't involve national security implications, this designation signifies that no single division can unilaterally authorize the release of information. All relevant offices must provide their approval. The significance of this stems from the distinct concerns each office addresses. Legal departments are concerned with potential liabilities. Export control departments focus on adherence to technology transfer regulations. Communications departments prioritize message consistency and appropriate timing. Planetary defense departments aim to prevent public alarm. Scientific departments are focused on peer review processes and maintaining academic credibility. Achieving consensus among these diverse groups on what information to disclose and when is akin to herding cats uphill at a glacial pace. Adding to this complexity is the issue of hardware ownership. Consider the HiRISE instrument, a high-resolution imaging science experiment aboard the Mars Reconnaissance Orbiter. This instrument is managed by the University of Arizona under a contractual agreement with NASA. If HiRISE captures an observation, who holds ownership of the data? Is it NASA, due to their financial investment, or the University of Arizona, as the entity operating the instrument? In practice, data-sharing agreements are established to clarify these matters. However, these agreements were originally drafted for routine scientific operations and were not designed for situations where the data might be deemed sensitive or where the timing of its release carries political weight. The Gemini Observatory presents an even more intricate scenario. It operates as an international consortium with multiple nations holding ownership stakes. If Gemini observes an object and wishes to release the data immediately, but NASA advocates for a delay, the consortium's decision-making process becomes paramount. The European Space Agency, ESA, operates under its own distinct protocols, independent of NASA's review procedures. Consequently, if an ExoMars orbiter captures images of an object, ESA possesses the autonomy to release them according to their own timeline. This is precisely what occurred, leading to the availability of ESA's imagery online while NASA's counterpart remains under review. This disparity generates friction. Academic institutions aspire to publish their findings, as this is fundamental to career advancement. Discovering something significant necessitates its swift dissemination to preempt competitors. However, NASA's Communications Division mandates that university partners await clearance. Universities are prohibited from independently publishing raw data on their websites without navigating the established channels. Envision the protracted email exchanges. A lead researcher at a university transmits images to their NASA liaison, proposing a release on a specific Tuesday. NASA Communications might respond with a request for additional time for calibration and review. The lead researcher might then point out that ESA has already made their findings public. Subsequently, NASA's legal department might intervene, emphasizing the need to verify the absence of export control concerns. The scientific team, meanwhile, might argue that this is basic astronomical observation and question the relevance of export control. This cycle of requests and responses perpetuates, leading to days, even weeks, of the data remaining in limbo. Further complicating matters are additional gating factors. If an object presents any potential risk to Earth, even a theoretical one, the Planetary Defense Coordination Office assumes oversight. They are responsible for assessing the threat level before any information is publicly disclosed. This is not an attempt to conceal danger, but rather a necessary step to comprehend the situation before it can be communicated effectively. International obligations introduce another layer of complexity. The United States is a signatory to various space treaties and agreements, some of which include provisions for sharing information concerning hazardous objects, or those with potential implications for other nations. Before NASA can release certain types of data, legal consultation with international partners may be required. Furthermore, budgetary realities play a role. NASA's funding is determined by Congress, and appropriations committees conduct hearings. If NASA releases data that sparks a media frenzy shortly before a budget hearing, the implications for their funding request are significant. Politicians generally prefer to avoid unexpected developments, particularly those that elicit concerned calls from constituents. Consider this hypothetical situation. NASA possesses data concerning an object that reveals genuine anomalies. While they intend to release it eventually, a budget hearing is scheduled for the following month, and there is a threat of a government shutdown. The communications office might inquire, could we postpone the release until after the hearing? Can we control the timing to prevent an issue from arising at an inopportune moment? This is not indicative of a conspiracy, but rather a pragmatic consideration of political dynamics. However, from an external perspective, it appears as deliberate delay, suggesting an attempt to conceal information. The longer such delays persist, the more suspicious the situation becomes. There is also a less frequently discussed legal dimension. Export control regulations, such as the International Traffic in Arms Regulations, ITAR, and the Export Administration Regulations, EAR, extend their reach internationally. ITAR can apply to satellite imagery if it possesses a sufficiently high resolution. EAR may be applicable to certain categories of scientific data. If NASA's observations of the object include high-resolution imaging, technical details about sensor capabilities, or any information that could conceivably be used to reverse engineer U.S. space technology, then an export control review becomes mandatory. Such reviews are time-consuming. It might seem far-fetched for this particular object to fall under these regulations, given it is an astronomical observation. However, if the object exhibits features that appear non-natural, or if there is any possibility that NASA's observations could be interpreted as indicative of technology, then the situation enters a legally ambiguous territory. The concept of national security clearance for unidentified anomalous phenomena alone warrants attention. The U.S. government has publicly acknowledged the existence of an office dedicated to investigating unexplained observations. If the object in question meets certain criteria, could it necessitate a briefing for that office? Could it require classified analysis prior to public dissemination? The extent of this possibility remains unknown. However, its existence within the existing legal framework implies potential delays and restricted access to information. This does not mean NASA is deliberately withholding information from the public, but rather that they are operating within constraints that are largely unrecognized by the general populace. The challenge arises when these restrictions, though perhaps institutionally sound, are not lifted in a timely manner. What if the public perceives these restrictions as being in place for improper reasons? Part 5, The Risk Spectrum, explores NASA's potential nightmare scenario. On one extreme lies the risk of disclosing too much information, and on the other the risk of prolonged silence. Navigating this requires NASA leadership to find a path that avoids catastrophic outcomes. Scenario 1. NASA releases data indicating that the object possesses features that could be interpreted as artificial structures. Let's examine the ramifications. The press release is issued, and within minutes, it becomes the leading news story across all outlets. Within hours, social media is ablaze with discussion. Proponents of such theories feel vindicated. Skeptics scramble to reevaluate, and conspiracy theorists assert their prior claims. Scientists attempt to inject caution, explaining that unusual characteristics do not inherently signify artificiality, but their measured pronouncements are drowned out by more vocal opinions. Cable news channels feature pundits lacking expertise in astrophysics, but possessing strong viewpoints. The discourse rapidly shifts away from the actual data presented by NASA. Individuals begin making assertions that far exceed the scope of NASA's findings. Other governments demand explanations, questioning whether NASA possessed prior knowledge, what other information is being withheld, and if this represents a threat. Religious communities react diversely, with some interpreting it as evidence of divine creation's breadth, and others viewing it as an existential challenge. Social media divides along predictable lines. Within 72 hours, the narrative evolves into something entirely divorced from the original data. NASA finds itself dedicating all its resources to rectifying misinterpretations, clarifying that anomalous features do not necessarily imply intelligence, and striving to restore clarity amidst overwhelming noise. Their credibility suffers, not due to error, but because they are unable to control the narrative. Scenario 2. NASA continues to delay the release of information. Weeks turn into months, and scheduled public release dates are repeatedly postponed. Other entities, such as ESA, private observatories, and amateur astronomers, begin publishing their observations. However, NASA, the agency that should be at the forefront, remains silent. Rumors proliferate, and online networks dedicated to speculative theories intensify. YouTube channels focusing on space mysteries gain millions of views, connecting disparate pieces of information and identifying non-existent patterns. In the absence of official data, speculation fills the void. Legitimate scientists express growing frustration, as they are unable to publish their research while awaiting NASA's official release. Academic careers are hindered, and papers languish in review because the underlying data has not been officially confirmed. Non-scientific voices begin to dominate the discourse, with individuals who project confidence but are factually incorrect gaining more traction than those who are meticulous and accurate. The conversation becomes compromised. When NASA eventually releases the data, whenever that may be, a significant portion of the public will have lost trust in the agency. The delay itself will have been interpreted as evidence of a conspiracy. Now let's consider this from a cost-benefit perspective. The immediate risks versus the long-term damage to reputation. If NASA releases information prematurely, they face immediate chaos, but potentially preserve their long-term credibility. The narrative would be, "We disclosed what we understood as soon as we grasped it. We were transparent." However, if the resulting chaos is severe, or if misinterpretations lead to real-world panic or misguided policy decisions, then transparency comes at too high a price. Conversely, if NASA delays, they avoid immediate chaos, but risk eroding public trust over the long term. The rationale would be, "We were proceeding with caution and conducting our due diligence." However, if the delay is excessively prolonged and appears to be an attempt at concealment rather than investigation, caution can be perceived as complicity. There are also legal repercussions to consider. Congress could initiate hearings, presenting a scenario where NASA's administrator faces senators questioning the agency's delay in releasing information about an interstellar visitor. Imagine attempting to explain intricate institutional review processes to politicians under pressure from their constituents to provide answers. International partners might begin to question their collaboration with NASA. If NASA is perceived as withholding information for extended periods, why should they be included in real-time observational efforts? The intricate network of scientific cooperation, painstakingly built over decades, could begin to unravel. Furthermore, the scientists themselves face significant professional repercussions. A researcher who observed the object and whose data remains stalled in NASA's review process cannot publish or present at conferences. Competitors at other institutions, not subject to the same review procedures, advance while they are compelled to wait. However, if NASA releases information prematurely and it later proves to be inaccurate or misinterpreted, the peer review process becomes a formidable challenge. Their reputation could be damaged, and future funding could be jeopardized. The cost of error in scientific endeavors is substantial. There is also a psychological dimension that is often overlooked. NASA's institutional culture is founded on the principles of accuracy, authority, and being a reliable source of information. Acknowledging uncertainty regarding the object's nature undermines this authority, revealing a lack of definitive answers within an organization expected to possess them. However, the public can generally accept uncertainty if it is communicated effectively. People understand that science does not have all the answers. What they find unacceptable is the perception of being deliberately kept in the dark. The appearance of secrecy is more detrimental than the admission of ignorance. Thus, NASA is in a predicament. Releasing too much information risks chaos, while waiting too long risks fostering conspiracy theories. With each day of delay, the pressure intensifies. Each day that other agencies release their findings, the comparison becomes more stark. Why is everyone else transparent except NASA? Underlying all of this is a deeper concern: the fear that acknowledging uncertainty about the object could embolden those who seek to undermine scientific authority in general. In an era where scientific institutions are already under scrutiny, where expertise is frequently challenged, and where misinformation spreads more rapidly than truth, NASA must consider that demonstrating uncertainty about the object might encourage those aiming to dismantle scientific authority altogether. This presents an insurmountable challenge, not merely managing a single anomalous phenomenon, but also navigating its broader implications for science, policy, public trust, international cooperation, and the very notion that we can comprehend the universe through diligent observation and reasoned analysis. Beneath the surface, whispers, leaks, competing theories, and withheld information from insiders persist. This is precisely where our investigation will now proceed. Part 6. Insider leaks and speculative threads. A phenomenon occurs within scientific communities when something of notable interest is developing. These are the informal discussions in hallways, the casual remarks at conferences, and blog posts that, while carefully worded to avoid definitive statements, manage to convey a great deal. With this particular object, such whispers began almost immediately. By frequenting astrophysics forums, reading comments on preprint servers, and paying attention to what scientists say when they believe they are not being directly overheard, one can discern a certain atmosphere. Unusual brightness dips that don't align with fragmentation models. One comment buried in a discussion thread on an astronomy subreddit might state, "Tail structure exhibits undulations inconsistent with gravitational dynamics." Another, from a comment section under a preprint paper. These are not official pronouncements, but rather subtle clues. Within the technical literature, references exist to unexplained residuals in imaging data. The phrase unexplained residuals carries significant weight, indicating the presence of something in the images that cannot be attributed to known phenomena. It could be instrumental noise, a calibration error, or it could be genuine. Some individuals have been more vocal in their speculation. Avi Loeb, the Harvard astronomer known for his openness to the possibility of artificial extraterrestrial objects, has shared his views, presenting this object as another instance where the scientific community may be too quick to assume natural explanations when the data doesn't quite fit. it is crucial to state unequivocally that these are opinions, not institutional statements. Loeb is a scientist with considerable credentials and expertise, but he speaks for himself, not for NASA or the broader astrophysics community. However, his willingness to publicly pose uncomfortable questions places pressure on those who are more discreet in their private deliberations. What might internal memos contain? We do not have access to actual leaks, but we can formulate educated conjectures based on the typical operational procedures. An anomaly flagged during routine data review. A request from the science team for reanalysis to identify potential non-natural motion signatures. A recommendation to defer public release pending secondary confirmation from an independent facility. This is speculative, but it represents the kind of cautious, qualified language that would likely be employed, acknowledging the need for further investigation without committing to any particular interpretation. Internal disagreements are almost certain, as this is how scientific inquiry functions. Some researchers examine the data and perceive exotic but natural processes, advocating for release with appropriate caveats. Others interpret the same data as requiring extraordinary caution, urging further analysis before any public disclosure. Imagine the flurry of emails exchanged. A principal investigator at one telescope facility might state, "We have confirmed the observation. The anomaly is real. We should publish." A representative from NASA Communications might respond, "Coordination with legal and planetary defense is required before any release." The principal investigator might push back, noting that ESA has already published their findings and that delaying would make NASA appear to be concealing information. The communications office might retort, "That decision is beyond our purview." These are not leaks. They are the inevitable tensions that arise when multiple stakeholders, with divergent priorities, attempt to navigate uncharted territory. External agencies published more rapidly, partly because they operate under different constraints. ESA is not accountable to the U.S. Congress, nor are they subject to the same export control regulations. They do not possess the same institutional history of past controversies, where premature disclosures led to problems. Consequently, they can proceed more quickly. This does not imply recklessness. It suggests they are operating within a different risk environment. Universities that manage NASA instruments find themselves in a mediating position. They value academic freedom and the ability to publish, but are also bound by their contractual obligations to NASA. As a result, they may push against these constraints, but are ultimately required to comply. The data may be ready and papers drafted, but they remain in preliminary form, awaiting clearance that could take weeks or months. Throughout this process, there remains the possibility that someone, somewhere, will decide that the public has an inherent right to know, that the scientific imperative for transparency outweighs institutional concerns about timing. A leak could occur. Someone might upload raw data to an anonymous server or send images to a journalist. As far as we are aware, this has not yet happened. However, the longer the lockdown continues, the greater the likelihood of such an event, given that scientists, as a general rule, advocate for openness, peer review, public data access, and the free exchange of ideas. When they are compelled to withhold interesting findings, pressure mounts. The speculative discussions online gain their own momentum. Reddit hosts extensive threads analyzing every fragment of released information. Twitter features amateur astronomers conducting their own observations and comparing them to the limited official data available. YouTube hosts channels dedicated to scrutinizing every frame of video and every data plot, searching for clues about what is being concealed. Most of this speculation is inaccurate. This is an inevitable consequence. Without access to the complete dataset, without understanding calibration processes, and without expertise in interpreting telescope data, amateurs will perceive patterns that do not exist and overlook significant details. However, their engagement, their commitment to seeking information, reveals an unmet appetite for data that NASA is not currently satisfying. This is how narratives escape institutional control. When official channels operate too slowly, unofficial channels emerge to fill the void. And once these unofficial narratives take root, they are exceedingly difficult to dislodge with factual information, even when that information eventually becomes available. Could this anomaly be not merely natural, but artificial? This is the question that looms over all this speculation. No one wishes to be the first to officially voice it, but in private conversations and carefully worded blog posts, the question is being posed. Until NASA provides data comprehensive enough to definitively answer it, the question will continue to be asked. Part 7. Technical possibilities. Let's lay out the facts. What are we truly dealing with? Let us construct a grid of hypotheses. On one side, we have natural explanations, and on the other, artificial possibilities. Let us then examine what each scenario predicts and what the data would indicate. Natural explanation number 1, exotic ices. Interstellar comets originating from other solar systems could possess compositions unknown to us, featuring different ratios of water ice, carbon dioxide, ammonia, and organic compounds. As these materials heat up and sublimate, they could produce jets that behave in unexpected ways. The underlying physics in this scenario is straightforward. Different volatile substances exhibit distinct sublimation temperatures. If a celestial nucleus possesses internal voids filled with highly volatile material concealed beneath a surface layer of less volatile matter, sudden eruptions could occur when that outer layer fractures. This could result in the expulsion of material in directions that might initially seem inexplicable until the internal structure is modeled. A second plausible natural explanation involves fragmentation caused by tidal forces. As a celestial body approaches the Sun, the intensity of these tidal forces escalates. These are the identical forces that influence Earth's oceans, generating tides. However, when applied to a comet, these forces can become potent enough to literally tear the object asunder. If 3I Atlas is undergoing fragmentation, this could account for abrupt alterations in its brightness, peculiar debris patterns, and perhaps even perceived motion that appears to defy gravitational influence, but is in fact the independent movement of constituent pieces. A third natural explanation is asymmetric solar heating. Comets are not perfectly spherical. They are irregularly shaped masses of ice and rock with varied surface characteristics. Different areas absorb heat at differing rates. This disparity can create imbalances in internal pressure, which then act like miniature rocket thrusters, propelling the object in unforeseen directions. This phenomenon is termed the Yarkovsky effect when observed in asteroids, and a similar mechanism could be at play here. Now, regarding the perplexing matter of the Sunwood jet, this is where the situation becomes truly intriguing. Typically, Jets are observed to orient away from the sun, as this is the region experiencing the most intense heating. Solar radiation exerts pressure on the gas and dust, expelling it from the sun's vicinity. Consequently, what could possibly cause a jet to be directed towards the sun? One potential reason involves rotational dynamics. If the nucleus is rotating and its active regions are situated in a precise configuration, it's conceivable that jets could appear to point sunward from specific vantage points. This would essentially be an optical illusion, where the jet is actually oriented sideways, but from our perspective on Earth, it seems to be aimed directly at the sun. Another possibility lies in interactions involving the solar magnetic field. If the solar wind carries magnetic fields that engage with electrically charged particles within the comet's coma, this could lead to intricate dynamics that diverge from straightforward pressure-based models. While this remains speculative, it falls within the established boundaries of physical laws. However, let's be candid. The alternative explanation, the one that makes everyone uneasy, is likely on everyone's mind. What if the observed phenomena are not entirely natural in origin? The first artificial hypothesis posits the existence of reflective panels. Imagine a constructed entity, not a solid mass, but rather a configuration with extensive surface areas designed to capture solar radiation. Similar to a solar sail, but perhaps damaged and in fragmented pieces, these tumbling surfaces would reflect light at various angles. This would account for variations in brightness that deviate from expectations for a solid nucleus. The second artificial hypothesis concerns propulsion residue. If an object were employing propulsion, even at very low levels, it would inevitably leave a detectable trace. This could manifest as heated gas expelled in specific directions, spectral lines that do not align with the typical composition of natural comets, or energy signatures that are inconsistent with solar heating alone. The third artificial hypothesis suggests modulated brightness as a form of signaling. This is where the speculation ventures into truly unconventional territory. However, if the observed changes in brightness exhibit periodicity, repeating in patterns that appear too regular to be coincidental, then the possibility of intentionality must at least be considered. Perhaps a beacon, a signal, or an attempt at communication. Let us now assess the plausibility. The magnitude of the brightness variations is a critical factor. If 3i Atlas is displaying significant fluctuations in brightness, we must reconcile the energy budget. Where is this energy originating from? If it stems from solar heating, the quantitative data must align. If not, then what is the source? Spectral signatures would offer insights into the object's composition. If observations reveal unusual spectral lines, indicating elements or molecules that are unexpected or present in abnormal proportions, this would constitute a significant red flag. Conversely, if the spectrum is entirely consistent with that of standard cometary material, it would lend support to natural processes. Inferring the object's shape from multiple perspectives would be highly beneficial. By observing the object from various directions over time, it would be possible to reconstruct its three-dimensional form. Does it appear irregular, akin to a natural comet, or does it exhibit geometric regularity that would be difficult to attribute to natural phenomena? Let us draw a parallel with Oumuamua. That object displayed anomalies in its light curve, brightness variations that suggested it might be elongated and possibly tumbling. Some researchers propose that it could be a solar sail, an artificial light sail constructed by an extraterrestrial civilization. While that proposition was and remains a subject of considerable debate, it falls within the scope of serious scientific discourse. The pivotal question concerning 3-through atlas is whether the observed brightness modulation is periodic. If one were to plot the brightness over time and identify recurring patterns with consistent frequencies, that would be a noteworthy finding. Natural rotation could indeed induce periodicity, but it would possess specific characteristics. Artificial modulation, on the other hand, might manifest differently, potentially exhibiting nested frequencies or patterns that deviate from simple tumbling motions. However, we must confront a significant challenge: the issue of automated calibration software. Modern astronomical instruments leverage artificial intelligence and machine learning to process raw observational data. These systems are adept at filtering out noise, compensating for atmospheric disturbances, and eliminating the effects of cosmic ray impacts. While remarkably sophisticated, they are not infallible. Occasionally, they can generate artifacts, illusory features that appear real in the processed data, but do not correspond to actual phenomena. The risk associated with calibration is a serious concern. Sensor artifacts can easily be mistaken for genuine signals. The impact of cosmic ray noise on a detector can resemble a sudden surge in brightness. Furthermore, post-processing filters, designed to accentuate specific features, may inadvertently create patterns that were not present in the original data. This underscores the paramount importance of verification. Multiple independent observations are essential, ideally from different instruments employing distinct calibration systems. If 3 separate telescopes consistently detect the same anomaly, it is likely a genuine phenomenon. However, if only a single instrument observes it, one must entertain the possibility of an instrumental artifact. Therefore, what lines of evidence would strengthen the artificial hypothesis? Firstly, consistent spectral anomalies that cannot be readily explained by known chemical processes. Secondly, imaging data revealing geometric features that exhibit regularity or symmetry, exceeding what is typically produced by natural phenomena. Thirdly, observed motion that appears to contravene the conservation of momentum unless active propulsion is at play. Fourthly, modulated signals displaying information-rich patterns that are too complex to be attributed to random chance. What would serve to disprove the artificial hypothesis? Essentially, identifying natural explanations that adequately account for all the observed data. If a model can be constructed wherein exotic ices, fragmentation, and rotational dynamics collectively explain all the observations, then the artificial hypothesis becomes unnecessary. Occam's razor dictates that the simpler explanation is preferred, unless the data unequivocally compels a more complex one. The predicament faced by NASA lies in navigating this uncertain middle ground. The data presents anomalies, but it remains unclear whether these anomalies necessitate extraordinary explanations. Further observations would undoubtedly be beneficial. Extended monitoring as the object traverses different segments of its orbital path. Spectroscopic analysis conducted with enhanced resolution. Imaging from multiple viewpoints to facilitate the construction of more refined shape models. However, a significant institutional hurdle exists: the open consideration of artificial hypotheses prior to the acquisition of conclusive evidence can be career-ending for many scientists. Such individuals risk being labeled as eccentric. Their research papers may struggle to gain publication in prestigious journals, and their funding prospects could diminish significantly. Consequently, even if a scientist within NASA suspects that the data points towards something unusual, they are likely to exercise extreme caution in how they articulate their findings. The prudent course of action is to state that anomalies have been observed which warrant further investigation. This approach is both accurate and non-committal, leaving all possibilities open without making extraordinary claims. It effectively buys time for additional data acquisition, more thorough analysis, and the gradual development of expert consensus. However, this cautious approach carries its own set of drawbacks. It can foster suspicion and lead to speculation about hidden information. It allows conjecture to flourish unchecked because the official channels are not providing sufficient data to constrain the discourse. Can this anomaly be attributed not merely to natural processes, but to artificial origins? We do not possess a definitive answer. That is the honest assessment. The uncertainty stems from insufficient data, or perhaps from data that has not been fully analyzed, or even from analyses that have not yet been made public. This gap between established knowledge and disclosed information is the very source of the current tension. The subsequent sections will delve into the institutional and legal complexities surrounding the very act of posing these questions. It turns out that contemplating the possibility of an interstellar visitor being artificial is not solely a scientific inquiry. It also encompasses political, legal, and institutional dimensions, touching upon everything from international treaties and congressional oversight to the fundamental underpinnings of our understanding of our place in the cosmos. Part 8. International and institutional friction. The European Space Agency released its imagery of 3I Atlas on the 23rd of July, 2025. The Gemini Observatory followed suit on the 25th of July. Japan's Subaru telescope published its observations on the 27th of July. Meanwhile, NASA's contributions remained under review as of mid-August. To provide precise timestamps, ESA's CASIS instrument aboard the ExoMars Trace Gas Orbiter captured images at 13:47 Coordinated Universal Time on July 22nd. These images were accessible in the public archive within 24 hours, representing standard processing, standard review, and standard release. Gemini South in Chile conducted observations of 3I Atlas on July 24th, utilizing its high-resolution imaging spectrograph. The resultant data appeared on their public server on July 25th, a turnaround time of 48 hours from observation to public release. Again, this was entirely routine for them. NASA's Hubble Space Telescope observed the object on July 20th, 2 days prior to ESA's observations and 3 days before Gemini's. Where are those images? As of the second week of August, they are not in the public archive. They are undergoing review. This represents a 3-week delay for an observatory that typically releases data within days of observation. Why this disparity? A portion of the explanation lies in structural differences. ESA operates under distinct regulations. It functions as an independent agency representing 22 member states. Its data release policies are dictated by European agreements, not by United States regulations. ESA possesses its own review processes, its own legal frameworks, and its own political pressures, though these differ from those faced by NASA. The Gemini Observatory is an international partnership involving the United States, Canada, Chile, Brazil, Argentina, and South Korea. It is governed by a board representing all participating nations. When Gemini intends to release data, it requires board approval. However, this is a considerably simpler procedure than NASA's multi-layered review process, because the partnership agreement was formulated with the objective of scientific transparency. NASA is accountable to the United States Congress. Its budget is derived from congressional appropriations. It is subject to United States export control laws and falls under the oversight of multiple committees in both the House and the Senate. Consequently, when NASA releases data, its considerations extend beyond purely scientific matters to encompass political implications, funding concerns, potential legal liabilities, and national security ramifications. United States export control regulations are more far-reaching than many individuals realize. The International Traffic in Arms Regulations, commonly known as ITAR, were established to prevent the proliferation of military technology to adversaries. However, these regulations can be applied to space systems due to the dual-use applications of certain space technologies. High-resolution imaging, for instance, could potentially reveal the capabilities of United States reconnaissance satellites. The Export Administration Regulations, or EER, pertain to items that are not classified as military hardware, but nonetheless possess strategic value. Scientific data can be subject to EER if it involves sensitive technologies, or could be utilized for reverse engineering systems that provide the United States with a competitive advantage. On the surface, it seems unlikely that 3-through Atlas would trigger these concerns. It is, after all, an astronomical observation of a natural or possibly natural celestial object. However, if there exists even a remote possibility that the observed phenomena are not natural, then the situation enters ambiguous territory. If NASA's images reveal features that could be interpreted as indicative of artificial construction, does this carry national security implications? Perhaps. What if other nations express interest in dispatching probes for investigation? What if there is technology present that could be recovered? In such scenarios, an astronomical observation could transform into a matter of strategic importance. Furthermore, the question of jurisdiction arises. NASA's Planetary Defense Coordination Office is tasked with tracking near-Earth objects that pose a potential collision risk. However, 3-3 Atlas is on an interstellar trajectory. It does not pose an immediate threat of impact with Earth. Therefore, does planetary defense have any purview over the dissemination of information concerning this object? The answer is nuanced. While planetary defense does not possess formal jurisdiction over interstellar objects, it exerts informal influence due to its role as the NASA office responsible for assessing threats emanating from space. If an interstellar object exhibits anomalous behavior, the Planetary Defense Division is keen to be informed. Their objective is to ascertain whether it represents any form of risk, even if that risk is not an immediate collision. Gray areas permeate the bureaucratic landscape, with no clear directive on who makes specific decisions. Mission scientists advocate for scientific autonomy. Communications officers prioritize controlled messaging. Legal departments aim to minimize liability. Planetary defense focuses on threat assessment. International affairs endeavors to maintain positive relationships with partner agencies. At the apex, NASA leadership strives to balance these competing interests while diligently avoiding any significant missteps that could jeopardize the agency's future. Here is a concrete illustration of how this friction manifests. Suppose an observatory in Europe wishes to share raw data with NASA scientists. Such data sharing typically occurs routinely under existing agreements. However, what if NASA's legal counsel advises that before accepting this data, it must be determined whether it falls under export control restrictions. The European counterparts would likely respond by asserting that it is astronomical data, inherently scientific in nature, and question why export controls would be applicable. NASA's legal department might counter that it could potentially reveal sensitive features. Suddenly, an international incident is brewing. The Europeans might perceive NASA as being overly cautious, while NASA might believe the Europeans do not fully comprehend the legal constraints under which they operate. Scientific collaboration then becomes collateral damage. Congressional oversight introduces an additional layer of complexity. Imagine a member of Congress becoming aware that NASA has made an unusual observation. They possess the authority to demand a classified briefing. NASA is legally obligated to comply. However, the act of providing classified briefings to Congress signifies an acknowledgement that there is indeed something of a classified nature. This acknowledgement, in itself, can generate complications, as it necessitates justification for withholding public access to data deemed significant enough for a congressional briefing. There is precedent for this. Following the encounter with Oumuamua, congressional inquiries were initiated. While not public in nature, certain lawmakers privately raised questions. They sought to ascertain whether NASA had thoroughly considered all potential explanations, including indeed the possibility that the object was not natural. NASA's response during that period was characterized by careful deliberation. They elucidated the scientific consensus, presented the natural explanations that aligned with most of the available data, and emphasized the principle that extraordinary claims necessitate extraordinary evidence. Nevertheless, those discussions did occur, and their occurrence establishes a precedent. Consequently, if 33 Atlas exhibits comparable or more pronounced anomalies, one can anticipate heightened congressional interest. And once Congress begins to pose questions, NASA's discretion in managing information on its own timeline diminishes. A hypothetical yet informed quote might encapsulate this sentiment. The European Space Agency had fewer review layers, so their version of the images was online while NASA waited for lawyers to approve every pixel. It's not that we're concealing anything. It's that we cannot release anything without multiple sign-offs, and obtaining those sign-offs requires time. This statement conveys frustration, likely emanating from a scientist eager to conduct research, but constrained by institutional bureaucracy. It is a sentiment probably echoed in correspondence and casual conversations across NASA facilities. The broader implication here is that institutional friction is not a matter of conspiracy, but rather of inherent complexity. The intersection of multiple agencies, diverse stakeholders, and disparate sets of regulations, all operating in ways that were never originally conceived for such a unique situation, creates challenges. The existing systems were designed for routine operational procedures, and they are now being subjected to immense stress by an event that is far from routine. Historical precedents demonstrate a recurring pattern. The subsequent sections will explore these precedents, examining instances where NASA delayed or withheld data, not due to concealment, but because institutional friction rendered timely release either difficult or impossible. Understanding these past occurrences will shed light on what might be transpiring currently. Part 9. Precedent Cases and Legal Frameworks. On October 19, 2017, the Pan-STARRS telescope in Hawaii detected an object exhibiting unusual characteristics. It was moving at an exceptionally high velocity, far exceeding that of a typical asteroid. Within a matter of days, astronomers calculated its trajectory, confirming that it was on a hyperbolic path. This marked the first confirmed interstellar visitor from beyond our solar system. It was given the Hawaiian name Oumuamua, meaning scout or messenger. NASA initiated observations using every available telescope, including Hubble, Spitzer, and various ground-based observatories. They meticulously gathered data on its motion, brightness, and spectral composition. Subsequently, a peculiar finding emerged. The object was exhibiting a slight acceleration, deviating from the path that would be predicted by gravity alone. This was termed non-gravitational acceleration. While comets do exhibit such behavior due to outgassing providing thrust, Oumuamua displayed no signs of outgassing. There was no visible coma, no tail, and no spectral evidence of sublimating volatiles. This raised the question, what was propelling it? The scientific papers detailing these findings were published months after the initial detection. These months were characterized by extensive internal debate, peer review processes, and careful linguistic formulation. When the acceleration was finally announced, the language employed was exceptionally cautious, describing it as unexplained acceleration consistent with, but not definitively attributed to, outgassing below detection limits. Some scientists proposed exotic explanations. Perhaps it was a hydrogen iceberg that would outgaze without leaving visible traces. Alternatively, its shape might have been akin to a pancake or a solar sail, allowing for propulsion via light pressure. And then a proposition that brought Avi Loeb into the conversation. What if it were artificial? Loeb's proposal garnered significant media attention, with headlines proclaiming that Harvard astronomers suggested Oumuamua could be an alien spacecraft. The broader scientific community reacted with considerable opposition. The majority of astronomers considered natural explanations, however unconventional, to be more plausible than leaping to artificial conclusions. However, Loeb persisted, authoring papers, granting interviews, and eventually publishing a book. He argued that science should remain open to all possibilities, and that dismissing the artificial hypothesis outright was unscientific. NASA's response throughout this period was one of deliberate reserve. They did not endorse Loeb's theories, but neither did they completely dismiss them. Their approach was to remain tethered to the data, presenting observations and outlining potential explanations, while emphasizing the need for further study. This represented the safe, institutional stance. However, what is particularly noteworthy is that in the years following the Oumuamua event, it became apparent that NASA's internal discussions were more open than their public statements suggested. Conversations took place regarding whether more should be done to investigate the artificial possibility. Debates occurred concerning the appropriate level of speculation for a scientific agency, and concerns were raised about the potential impact of public speculation on funding and credibility. These internal tensions never escalated into a public crisis, primarily because Oumuamua departed. It traversed the Sun's vicinity and continued its trajectory out of the solar system, moving too rapidly for any spacecraft to intercept. The data collected represents all that will ever be available unless another similar object is detected. Consequently, the controversy eventually faded from public attention, despite remaining unresolved scientifically. Mars offers further illustrative examples. In 2013, The Curiosity rover detected unexpected spikes in atmospheric methane. The presence of methane on Mars sparks significant interest, as it could either point to the existence of life or stem from purely geological processes. Regardless of its origin, the discovery carries considerable weight. NASA chose to defer making public the initial detection of this gas. A substantial period elapsed between the first measurement and the official announcement. The rationale behind this delay was the imperative to thoroughly verify the findings, eliminate any possibility of contamination, confirm the instrument's proper functioning, and fully comprehend the implications before formally declaring its existence. When the announcement was finally made, it garnered widespread attention, with headlines proclaiming Mars Curiosity's discovery of methane. However, NASA's official statement was carefully worded, noting that methane had been detected in the Martian atmosphere, with its source remaining unknown and potentially being either geological or biological, necessitating further investigation. They provided just enough verified information to be truthful, without overstating their conclusions. Some members of the scientific community voiced criticism regarding the postponement, questioning the rationale for withholding data for months before releasing it for community analysis. Nevertheless, NASA leadership defended their cautious approach, emphasizing the critical importance of accuracy, stating that a premature announcement later proven incorrect would irrevocably damage their credibility. Looking back further, to the Apollo era, there were instances where data was classified for national security purposes. Certain early Apollo missions were equipped with cameras that doubled as reconnaissance tools. While these cameras captured images of the moon, they possessed the capability to photograph Earth from orbit, overlapping with the functions of spy satellites. Some lunar photographs were initially withheld or restricted because they revealed technological capabilities deemed classified. The scientific findings were made public, but the technical specifications detailing how these images were obtained remained secret for many years. Astronauts underwent debriefings by intelligence agencies and held security clearances, meaning some of their documented observations were subject to classification review. This is not a matter of speculation, but a documented historical fact. Space exploration and national security have always been closely linked. The same rockets that launch scientific satellites can also carry military payloads, and the technologies used to study planets can also be employed to monitor adversaries. A complete separation of these domains is not feasible. Currently, formal legal frameworks govern these interconnections. NASA operates under the Space Act of 1958, the legislation that established the agency and defined its mandate. A provision within this act permits the classification of certain NASA activities if deemed necessary for national security. While this clause has been invoked infrequently, its existence is significant. More recently enacted statutes concerning planetary defense assign NASA the responsibility of tracking potential threats originating from space. Although these statutes do not explicitly mention interstellar objects, they could be interpreted to include them if such an object posed any perceived risk. United States national security review processes involve multiple government agencies. The National Space Council is responsible for coordinating space policy across various government departments. The Office of Science and Technology Policy provides the President with advice on scientific matters. The intelligence community monitors foreign capabilities and potential threats. If an event in space raises concerns that transcend these specific jurisdictions, the review process can be elevated beyond NASA's direct purview. Could the object designated 3I Atlas fall under these frameworks? It's a possibility. If its unusual characteristics suggest the presence of technology, even if that technology is not of human origin, there might be grounds for a national security review. This wouldn't necessarily be due to an immediate threat, but rather due to strategic interests. Publicly accessible documents illustrate the procedures for flagging anomalous data. NASA's own data release policy stipulates that unusual observations require authorization from a higher authority before public dissemination. The term anomalous is broadly defined as significantly deviating from established predictive models or expected outcomes. 3I Atlas fits this description, as its observed behavior deviates from standard models of celestial object behavior. Therefore, according to NASA's own policy, elevated authorization is required. This is not conjecture, but established procedure, and such procedures inherently require time. While these protocols are being followed, the public waits and speculates. The speculative leap arises. What if 3I Atlas triggered multiple review criteria simultaneously? Imagine it flagged for planetary defense due to trajectory uncertainties, for export control considerations because of its imaging resolution, for scientific review due to its unusual characteristics, and for public affairs attention owing to significant media interest. Each of these triggers would introduce a delay, and multiple triggers would compound the problem. This scenario could potentially explain the ongoing lack of a comprehensive NASA release. The explanation might not be a deliberate attempt to conceal information, but rather the inevitable outcome of the bureaucratic machinery processing the situation through various channels, each with its own timeline. This situation directly contributes to the narrative conflict between disclosure and credibility. NASA finds itself caught between the imperative of transparency and the necessity of institutional self-preservation. Releasing information too soon risks being proven incorrect, while waiting too long risks eroding public trust. With each passing day that elapses without a definitive resolution, the tension escalates. Part 10. The narrative of disclosure versus credibility. NASA's institutional identity is fundamentally built upon a foundation of accuracy and achievement. They are recognized as the agency that successfully landed humans on the Moon, deployed rovers on Mars, piloted spacecraft past Pluto, and deployed telescopes capable of observing the very edge of the observable universe. Consequently, when NASA issues a statement, it carries significant weight and is generally believed. This credibility represents the agency's most valuable asset. However, credibility is inherently fragile. A single major error, a significant public misstep, can undermine decades of accumulated trust. In the current era of social media, mistakes are not merely damaging to reputation. They can become viral memes, indelible moments etched into the collective cultural consciousness. Therefore, when NASA encounters phenomena like 3I Atlas, something truly extraordinary, they face a profound dilemma. The inherent scientific drive is to share data openly, to invite rigorous scrutiny, and to allow the broader scientific community to analyze and debate findings. Conversely, the institutional imperative is to safeguard credibility, to make only claims that can be unequivocally defended, and to maintain control over the official narrative. This is where the amplified voices of social media come into play. A figure like Lowe, whom we have previously mentioned, commands a following of hundreds of thousands across various platforms. When he posts about 3i Atlas, his audience is immediately informed. His willingness to engage in speculation and pose hypothetical questions makes him particularly compelling. He is not constrained by the institutional caution that governs NASA. He can articulate ideas that NASA scientists might entertain but are unable to express publicly. Other voices contribute to this discourse. Popular science communicators, YouTube channels boasting millions of subscribers, and podcasters reaching audiences larger than most established newspapers join the conversation. These creators are typically not acting with malicious intent. The vast majority have a genuine passion for space science. However, they operate within an attention economy where the most sensational interpretation garners the most views. Consequently, when NASA delays the release of data, these voices inevitably fill the void. They meticulously analyze the limited information available, enhance images in pursuit of hidden details, scrutinize timelines, track the release of information by different agencies, and construct theories about the reasons behind the delays. The absence of complete data allows for the hijacking of the narrative. In the absence of a comprehensive picture, individuals construct their own versions of reality, and these constructions are often far more dramatic than the actual circumstances, as drama is inherently captivating. YouTube creators produce videos with titles like, "What NASA Doesn't Want You to Know About 3i Atlas." Twitter threads go viral with questions such as, "Why is NASA hiding this interstellar anomaly?" Reddit communities dissect every available piece of information, searching for clues. Forums dedicated to unexplained phenomena add 3i Atlas to their growing list of potential evidence supporting extraterrestrial intelligence. None of this would likely occur, or at least gain such significant traction, if NASA's official channels were consistently providing timely and comprehensive updates. However, NASA is unable to do so because they are ensnared in review processes. Consequently, unofficial channels gain prominence, and once these narratives take root, they become exceedingly difficult to dislodge. Internally, within NASA, there are considerable tensions regarding how to manage this situation. Scientists advocate for open data access, as this is the fundamental principle of scientific inquiry. Collect observations, release them, allow the community to analyze them, and let consensus emerge through debate and peer review. Restricting access to data runs contrary to the core scientific culture. The communications staff, on the other hand, prioritize controlled framing. They understand that raw data presented without adequate context is highly susceptible to misinterpretation. Their goal is to release information accompanied by explanatory text, caveats, and carefully chosen language that facilitates public comprehension of what is being observed. Preparing such comprehensive materials naturally requires time. Senior leadership is focused on preserving long-term credibility. Their considerations extend to the potential institutional repercussions. If NASA were to release information that is later proven incorrect, or if they were forced to retract a significant claim, the ensuing damage could have ramifications for the agency for years to come. Future missions might face funding cuts, Congress could demand increased oversight, and public trust could erode significantly. These individuals are not acting with nefarious intentions. Rather, they are grappling with diverse, legitimate concerns, all attempting to navigate an exceptionally challenging situation. However, their internal disagreements result in paralysis. While they debate the course of action, progress stalls, and the delay itself becomes the central narrative. Here is a scenario that deeply alarms NASA leadership. Imagine a data leak occurs. An individual within the agency, perhaps driven by frustration over the delays, transmits raw data to a journalist. The journalist, lacking the full context, publishes the information. The images reveal ambiguous features that are open to multiple interpretations. Media outlets seize upon the most dramatic possible interpretation, leading to headlines such as NASA data suggests artificial structure in interstellar object. Within hours, NASA's communication channels are overwhelmed. Congressional offices demand immediate explanations. International partners feel blindsided. NASA is then compelled to spend days or even weeks attempting to correct the public record, explaining that the data does not actually depict what has been inferred, that the features in question could be natural phenomena, and that further analysis is required. Even after issuing a correction and releasing the complete dataset with appropriate context, a substantial segment of the public will likely retain their belief in the initial, more dramatic interpretation. They may perceive NASA's corrective actions as a cover-up. The agency's responsible attempt to clarify the situation is then twisted into evidence of a conspiracy, resulting in damage to its reputation and compromised credibility, all stemming from a data leak that occurred before the agency was prepared to properly frame the information. However, there is a counter-argument to this perspective. Perhaps NASA's silence itself constitutes a betrayal. By withholding data and prioritizing institutional protection over scientific transparency, are they betraying the very principles that legitimize their existence? Science is intended to be an open and transparent endeavor, where the pursuit of truth supersedes the preservation of reputation. If NASA chooses to prioritize credibility over disclosure, has it ceased to function as a scientific institution and transformed into merely a political entity? This debate is undoubtedly occurring internally within NASA. One can be certain of it. There are individuals within the agency who believe these delays are misguided, arguing that the public has a right to see observed phenomena, even if they remain uncertain. Conversely, others maintain that caution is paramount, asserting that certain information, once released, cannot be recalled. Both perspectives hold valid points, which is precisely what makes this situation so intractable. There is no definitively correct course of action. Every option carries inherent risks, and every decision has consequences. While NASA grapples with this complex dilemma, 3I Atlas continues its journey through the solar system, and the world collectively watches and waits. NASA does not operate in a vacuum. Other recent events in both scientific research and governmental affairs demonstrate that this tension between disclosure and control is a pervasive issue. The subsequent sections will explore analogous situations, instances where similar dilemmas have manifested in different contexts, as understanding these broader patterns can illuminate the current circumstances. Part 11. Parallel Case: AI-Driven Signal Detections. On May 20th, 2024, the Breakthrough Listen Project, a decade-long initiative dedicated to searching for evidence of intelligent life beyond Earth, announced an unusual finding. Their artificial intelligence-powered analysis system had identified an anomalous signal emanating from Proxima Centauri, our closest stellar neighbor, located just over 4 light-years away. The signal, designated BLC-1, was initially detected in April 2019, but it took several years to fully analyze. It appeared within a specific, narrow frequency band around 982 MHz and exhibited characteristics that made it challenging to dismiss as terrestrial interference or natural astrophysical phenomena. What is particularly relevant to our narrative is the extensive period between the signal's detection and its official announcement. 5 years elapsed. The signal was first detected in 2019, and the comprehensive scientific paper detailing the findings was not published until late 2024. This 5-year span was dedicated to verification, analysis, the systematic exclusion of alternative explanations, and the building of consensus among the research team. The extended duration was necessitated by the profound understanding among all involved that announcing a potential technosignature, a signal that could indicate the presence of technology from another civilization, would be an event of immense significance and potential impact. Absolute certainty was required to avoid error. Every conceivable natural explanation, every potential instrumental artifact, and every possible way in which the team might be misleading themselves had to be meticulously ruled out. The AI system responsible for flagging BLC-1 was specifically designed to detect patterns that human observers might overlook. This involved machine learning algorithms trained on millions of observations, enabling them to differentiate between interesting signals and background noise. However, AI is not infallible and can be susceptible to misinterpretation, particularly if trained on limited datasets, or if the signal's characteristics fall outside its established training parameters. Consequently, the Breakthrough Listen team conducted extensive manual checks. They reobserved the target celestial object, attempted to reacquire the signal, and rigorously compared it against known sources of terrestrial interference. They also modeled natural phenomena that could potentially generate similar spectral signatures. The findings underwent internal peer review, followed by external peer review. This layered approach ensured a high degree of verification. Even after all these rigorous steps, and following 5 years of painstaking work, the announcement itself was delivered with extreme caution. Candidate signal detected. Most likely explanation remains terrestrial interference, despite efforts to rule it out. Does not currently constitute evidence of extraterrestrial technology. Further observation planned. This exemplifies the responsible method for announcing a potential finding without making unsubstantiated claims. This serves as a template for the responsible disclosure of anomalous data. However, the cost of this caution was significant. 5 years of silence while the analysis was underway. During this period, the detection existed, but was not publicly known. Breakthrough Listen is a privately funded initiative supported by philanthropist Yuri Milner. They are not subject to the same governmental oversight as NASA and do not face the same political pressures. Nevertheless, they keenly felt the weight of their responsibility. They recognized that a premature announcement could severely damage the entire field of SETI, search for extraterrestrial intelligence, potentially hindering future funding opportunities and inviting ridicule that could set back the search for decades. Comparing this timeline and the internal institutional friction to the case of 3I Atlas reveals striking parallels. While the subjects differ, one involving a radio signal and the other an interstellar object, the fundamental dilemma remains the same. Both instances involve anomalies that, with a degree of imaginative interpretation, could suggest the presence of intelligence. Both involved AI or automated systems flagging unusual phenomena. Both triggered institutional hesitancy regarding the timing and manner of disclosure. The correlation is undeniable. When an observation appears exceptionally strange, deviating significantly from established expectations, the system's inherent response is to engage in further review and verification, necessitating increased caution. This is not indicative of a conspiracy, but rather of conservatism, the scientific and institutional equivalent of meticulously planning before acting. However, this conservative approach comes at a cost. While Breakthrough Listen spent 5 years verifying BLC-1, the public remained unaware of the potential discovery. The broader scientific community was also uninformed, precluding the possibility of collaborative analysis. The signal remained a secret, albeit one held for what were considered valid reasons. We are likely witnessing similar dynamics at play with 3I Atlas. The anomalous observations have triggered internal alarms within NASA, activating established review protocols. Scientists are likely undertaking the same type of verification that Breakthrough Listen conducted, systematically ruling out instrumental artifacts, modeling alternative explanations, and building a case to determine whether the object is truly unusual or merely appears so due to a lack of sufficient observational data on interstellar objects to establish what constitutes normal behavior. This process, by its nature, requires time. However, time is a resource that the public is often unwilling to grant. Unlike a radio signal that can be reobserved at any time, 3I Atlas is in motion. It is approaching perihelion, its closest point to the Sun, and will subsequently depart from our vicinity. There is a finite window of opportunity for observation, and this window is rapidly closing. Consequently, NASA faces a temporal pressure that Breakthrough Listen did not. Not only must they verify their observations with rigor, but they must also do so within a deadline dictated by celestial mechanics. This creates a significant constraint. High-quality analysis necessitates time, yet time is rapidly diminishing. This situation establishes a precedent for how entities involved in space science are likely to respond to signals that might indicate intelligence. The observed pattern is consistent. Flag the anomaly, verify its authenticity, hesitate before disclosure, initiate review processes, hesitate further, and then eventually disclose with maximum caution and minimal definitive claims. This pattern prioritizes avoiding error over being the first to report. It values reputation and accuracy over speed. Is this the appropriate balance? In an era of instant information dissemination, when the public expects real-time updates, and when competing nations might not adhere to the same stringent constraints, can NASA afford to proceed at a pace dictated by caution? Or does caution itself become a liability when it appears to be a means of concealment? We do not yet have definitive answers, but we are observing this pattern unfold in real time. Both AI-flagged anomalies and the behavior of interstellar objects are pushing the boundaries of how scientific institutions manage uncertainty. Both are exposing the inherent friction between the principles of disclosure and the imperative of maintaining credibility. Both are compelling the world to engage in conversations about governance, transparency, and the ultimate authority in deciding when humanity learns about potentially paradigm-shifting observations. The subsequent section will examine recent policy changes, including legislation and international agreements, that could potentially compel NASA to alter its current approach, making the existing methodology unsustainable. Part 12. Policy Spotlight, Space Governance, and Secrecy. On March 15th, the United States House Committee on Science, Space, and Technology convened hearings concerning mandates for open data access in federally funded space research. The proposed legislation, known as the Space Science Transparency Act, would stipulate that NASA and other relevant agencies must release observational data within 30 days of its collection, unless specific exemptions are granted. The proponents of this bill argue that research funded by taxpayers should be readily accessible to the public. They frequently cite instances where data has been withheld for extended periods, sometimes months or even years, thereby impeding independent verification efforts and slowing down the overall progress of scientific discovery. Their objective is to establish openness as the default standard, rather than a discretionary practice at the agency's discretion. NASA's response to this proposed legislation has been measured and cautious. While they express support for transparency in principle, they also emphasize the need for flexibility in situations where immediate release of data might be premature. Their concerns encompass issues related to data quality, the verification of calibration processes, agreements with international partners, and, in rare instances, national security considerations. As of August 2025, the bill remains in committee and has not yet been enacted into law. However, its very existence exerts pressure on NASA. If this legislation were to be passed, it would significantly constrain NASA's ability to maintain extended review periods for its data. A 30-day window from observation to release leaves very little room for the multi-layered verification processes we have been discussing. This legislative initiative is not the sole source of policy pressure. The international community is also moving towards more stringent requirements for open data sharing. The Committee on Space Research, COSPAR, an international body that coordinates space research activities among various nations, has been actively developing new guidelines for expedited data sharing, particularly for observations that could have implications for planetary defense or other matters of urgent concern. While these COSPAR guidelines are not legally binding, they exert considerable normative pressure. If the majority of major space agencies commit to rapid data release, NASA's reluctance to do so would likely result in negative public perception. International scientific collaboration is fundamentally dependent on mutual trust and reciprocity. If NASA were to develop a reputation for being slow or secretive in its data dissemination, partner agencies might become less inclined to share their own data in return. Furthermore, cybersecurity considerations introduce additional complexities to the process of data release. Space missions generate enormous volumes of data. The information is housed on servers susceptible to cyber intrusions. Prior to public dissemination, governmental bodies aim to confirm that all technical metadata has been purged, which could otherwise expose weaknesses in satellite systems or ground-based infrastructure. This is a genuine apprehension. China and Russia possess advanced cyber capabilities. If the raw data contains temporal information, orbital trajectories, or sensor specifications that could be reverse-engineered to understand the operational mechanisms of U.S. space assets, it poses a significant security threat. Consequently, before any release, a cybersecurity review is conducted to eliminate potentially sensitive metadata. This scrutiny requires time, typically measured in days rather than weeks. When combined with other review stages, these days accumulate, introducing another bottleneck in the process and contributing to delays in NASA's data release compared to agencies facing different threat landscapes. The Outer Space Treaty of 1967 also holds relevance. Article 11 of this treaty mandates that signatory nations inform the UN Secretary-General and the public about the nature, progression, and outcomes of their space activities. The wording is imprecise, leading to inconsistent enforcement. Yet it establishes a fundamental principle of transparency. If 3I Atlas exhibits genuinely anomalous characteristics, representing something unprecedented, there's a compelling argument that the treaty necessitates its disclosure. This would not be immediate or prior to verification, but eventually. NASA cannot indefinitely withhold information that could fundamentally alter our understanding of the universe without contravening international norms. These policy pressures are converging. Domestic legislation advocates for expedited releases. International guidelines promote increased openness. Treaty obligations mandate disclosure. All of this is occurring while NASA grapples with an observation that defies existing categorization. Should the Space Science Transparency Act be enacted, NASA will be compelled to adapt. They will need to optimize their review procedures. They must devise methods for swift data dissemination, while maintaining quality assurance. Developing clear protocols for what constitutes a valid exemption and what does not will be essential. 3I Atlas could serve as a pivotal test case. If NASA imposes further significant delays, or if they retain data when the legislation is up for a vote, lawmakers may cite this specific situation as justification for the bill's necessity. The public has a right to access this information. NASA has had months. What is the cause for their hesitation? This political pressure could precipitate a release before NASA feels adequately prepared. This brings us to the core predicament. Release data before certainty, risking factual errors, or await confirmation, risking political repercussions and policy changes that diminish institutional autonomy. There is also ongoing discussion regarding the establishment of an international framework for anomalous observations. This could involve a rapid alert system for space discoveries, with potentially far-reaching implications. Should any major observatory detect something truly unusual, a coordinated disclosure protocol involving multiple nations and agencies would be implemented simultaneously. This concept holds appeal as it diffuses accountability, relieving any single agency from the sole burden of announcing an extraordinary finding. However, it also introduces complexities in coordination. Achieving consensus among multiple nations on the timing and content of disclosures is challenging, given diverse political systems, varying cultural perspectives on transparency, and differing institutional risk appetites. Presently, such a framework is absent. Consequently, NASA is navigating this situation independently, or at least without a clear roadmap for managing it. They are making real-time decisions regarding an unprecedented event, under global scrutiny, and constrained by a multitude of overlapping policy frameworks. The overarching implication is that space governance is in flux. The established rules for routine operations are being tested by anomalies, escalating commercial activities, international competition, and public demands for greater transparency. 3I Atlas stands at the nexus of these converging forces. NASA's actions or inactions will likely shape the future trajectory of these policies. However, NASA is not merely confronting abstract policy challenges. They are also dealing with recent, tangible instances where orbital anomalies have generated similar tensions. The subsequent section will delve into one such case. Part 13. Anomaly in Earth Orbit Surveillance. February 9, 2025. The U.S. Space Force's Space Surveillance Network detects an unusual radar signature within geostationary orbit. The object materializes abruptly, was absent in prior scans, and exhibits reflectivity characteristics inconsistent with known satellites or debris. For 48 hours, its origin remains a mystery. Space Force analysts cross-reference the signature with their existing catalog. No match is found. They consult with satellite operators, none of whom have launched new assets into that orbital slot. Debris models are examined, but no explanation emerges. Subsequently, the object vanishes. It simply disappears from tracking, present in one orbital pass, absent in the next. No trajectory indicating orbital decay, no indication of deorbiting, just gone. On February 11th, Space Force issues a concise statement. Anomalous radar return observed in geostationary belt. Object no longer tracking. Likely instrumentation artifact or debris fragment below persistent tracking threshold. No threat to operational satellites. This brief statement offers no specifics regarding the object's characteristics, no radar data, and no imagery, serving merely to acknowledge the observation without substantive detail. The rationale for this minimal disclosure lies in the distinct operational protocols governing the Space Force compared to NASA. A significant portion of their activities pertains to national security. Their surveillance network serves scientific purposes, but its primary function is military, tracking adversary satellites, monitoring for anti-satellite weapon tests, and providing early threat warnings. When this network identifies an anomaly, the default assumption is potential military relevance. It could signify a new Russian satellite with stealth capabilities, a Chinese demonstration of orbital rendezvous technology, or debris from an undisclosed test. Military considerations take precedence. However, this situation becomes more intricate. Amateur satellite observers also reported peculiar phenomena during the same time frame. Discussions on specialized forums detailed unusual brightness events in that sector of the sky. Observers in Australia, South Africa, and South America all reported brief visual sightings. Their accounts corroborate the presence of an object, albeit without definitive identification. Thus, we have an officially minimal acknowledgement juxtaposed with more detailed, yet less authoritative, amateur observations. This disparity fuels rampant speculation. What was it? Why did the Space Force downplay it? What information are they withholding? Contrast this with the speed and transparency surrounding 3I Atlas. The Space Force transitioned from detection to public statement within 48 hours, albeit with limited information. NASA, however, is weeks into analyzing 3I Atlas, with no comprehensive statement. The divergence in timelines stems partly from differing mission objectives. The Space Force's mandate is to safeguard U.S. space assets and monitor potential threats. A rapid, generalized acknowledgement aligns with their operational imperatives, informing the public of an assessment without revealing sensitive capabilities or intelligence methodologies. NASA's mission is scientific exploration and public inspiration. A brief, uninformative statement is ill-suited to their objectives, as the public anticipates detailed explanations, context, and educational insights. A two-sentence report would be widely unsatisfactory. Nevertheless, This contrast underscores how even proximate anomalies become ensnared in the cycle of delay versus explanation. If the Space Force hesitates even regarding potentially militarily relevant orbital objects, it stands to reason that NASA would exhibit greater caution with an interstellar visitor possessing potentially more profound implications. The February anomaly also prompted internal reviews within both the Space Force and NASA. The necessity for coordination was assessed. Did the temporal proximity of the Earth orbit event and 3I Atlas's closest approach warrant investigation into potential connections? While highly improbable, due diligence demanded confirmation. Someone had to ascertain whether any link could exist between an interstellar object and an orbital anomaly. This verification process requires time, interagency communication, and collaboration among personnel in different bureaucratic structures to share data and eliminate unlikely, yet not impossible, scenarios. During this period of investigation, neither agency can fully disclose its findings, as the understanding of the situation is still evolving. Furthermore, the handling of this anomaly sets a precedent. The Space Force's response, rapid acknowledgement with minimal detail, raises the question of whether this will become the standard approach, or if the criticism regarding a lack of transparency will encourage future responses to be more open. Amateur observers expressed frustration, feeling they received no useful information. The official statement failed to clarify what they had witnessed, appearing dismissive, as if the agency was assuring them not to be concerned without addressing their observations. From the Space Force's perspective, however, their duty was fulfilled. The threat was assessed, deemed non-existent, and the public was informed of this conclusion. Providing further details would compromise their surveillance capabilities. While this calculus differs from NASA's, it is driven by similar underlying tensions. If NASA hesitates concerning an orbiting satellite anomaly, and the Space Force exhibits even brief reticence, why would they not exhibit even greater caution when confronted with something as unprecedented as an interstellar visitor exhibiting anomalous features? The Earth orbit case illustrates that hesitation is the norm rather than the exception. When an event deviates from standard operational procedures, every agency must navigate the inherent conflict between transparency and operational security, public curiosity, and institutional limitations. 3I Atlas is pushing these boundaries on a significantly larger scale, but the fundamental dynamics mirror those observed in Earth orbit. An unknown object with unusual characteristics, pressure for immediate explanation, and institutional imperatives for cautious action. These are not isolated incidents. They are interconnected by shared governance challenges, policy lacunae, and the ongoing struggle to balance competing priorities. Crucially, these events are unfolding at a time when scientific understanding itself is being challenged by revolutionary discoveries that disrupt established frameworks. Part 14. Scientific Revolutions Under Pressure. June 23, 2025. A team of astronomers announces the detection of an exoplanet atmosphere, displaying spectral signatures inconsistent with any known chemical composition. The planet, orbiting a star 240 light-years distant, exhibits absorption lines that do not correspond to oxygen, methane, water vapor, or any other common atmospheric constituent. This discovery is predicated on data acquired by the James Webb Space Telescope. comprising multiple observations over several months. The signal is robust, repeatable, and unlikely to be an instrumental artifact, yet no one can identify the molecule responsible for these spectral lines. The paper detailing this discovery adopts a notably cautious tone. Unidentified spectral features detected in transmission spectrum. Possible systematic effects cannot be fully ruled out. Alternative explanations include unknown photochemistry or instrumental calibration errors. Further observation required. This language encapsulates the scientific culture surrounding anomalies. Even with solid data and meticulous verification, a degree of reservation is expressed. Claims are tempered, and room is left for potential error, without sacrificing credibility. The rationale is that scientific reputations are built gradually and can be rapidly undermined. Announcing a groundbreaking discovery that proves incorrect can transform a scientist into a cautionary example, negatively impacting their career, subjecting future publications to heightened scrutiny, and increasing skepticism towards funding applications. Consequently, scientists engage in self-censorship, not by withholding data, but by moderating their language, emphasizing uncertainties, and encouraging alternative interpretations. This protective behavior, while rational given academic incentives, can impede paradigm shifts. If collective caution prevents the suggestion that existing models may be fundamentally flawed, the field can stagnate as novel ideas fail to emerge when individuals are reluctant to be the first to propose radical departures. The exoplanet atmosphere case is still progressing. As of mid-August 2025, several other research groups are attempting to observe the same planet to validate or refute the initial findings. This represents the scientific method in action: assertion, verification attempts, and the pursuit of consensus, albeit a slow process. It may take years to ascertain whether these spectral lines signify a genuine discovery or a measurement error. This situation draws parallels to NASA's predicament with 3I Atlas. The incentive structures are similar. Scientists examining the data may identify observations that challenge established models, but they are hesitant to publicly declare such findings without overwhelming evidence, given the severe consequences of being mistaken. Agency-sponsored scientific endeavors face additional constraints. When individuals are affiliated with NASA or receive NASA funding, they not only represent themselves, but also the institution. Their pronouncements reflect upon the agency, creating pressure to align with institutional messaging, avoid making speculative claims that could embarrass their employer, and adhere to approved communication protocols. This is not indicative of conspiracy, but rather organizational dynamics. Professionals within large institutions learn to exercise caution in their public statements, obtaining management approval, employing standardized language, and considering the potential interpretations and institutional implications of their words. While this approach functions effectively during ordinary times, ensuring consistent messaging and professionalism, it can become an impediment to truth-telling when genuinely anomalous events occur. Consider a NASA scientist analyzing 3I Atlas data and concluding that the observations deviate significantly from natural models, suggesting the real possibility of something extraordinary. Such a scientist faces a dilemma. They cannot simply broadcast their findings on social media, as this would violate their employment agreement. Disclosing information to journalists would likely constitute grounds for dismissal. Presenting findings internally would subject them to the aforementioned review process, ceding control over the timeline. Alternatively, they can moderate their conclusions, embedding their actual findings within carefully worded papers, replete with caveats, hedging, and alternative explanations, thereby avoiding undue attention. This safe path, however, risks delaying paradigm shifts. Scientific history is replete with instances where revolutionary ideas encountered initial resistance due to their challenge to prevailing paradigms. Continental drift was ridiculed for decades before plate tectonics gained acceptance. The bacterial origin of ulcers was initially rejected until irrefutable evidence compelled acceptance. Dark energy was perceived as improbable until the data became undeniable. In each case, the delay stemmed not from conspiracy, but from justifiable scientific conservatism. The principle that extraordinary claims necessitate extraordinary evidence places a high burden of proof, which is appropriate. However, this high threshold introduces friction, slowing the recognition of genuine anomalies. 3I Atlas may be forcing NASA into precisely this scenario. If the data genuinely indicates something paradigm-shifting, the institution faces pressure to downplay it until the evidence is unequivocally overwhelming. Yet, accumulating such comprehensive evidence is a time-consuming process. During this interim period, delays and cautious language inevitably fuel suspicion. This is the broader context in which NASA operates. It transcends a single comet or anomaly. It encompasses how scientific institutions manage uncertainty, balance caution with openness, and navigate the space between preserving truth and safeguarding reputation. The exoplanet atmosphere case is likely to be resolved within 1 to 2 years, either through confirmation and explanation of the spectral features or their attribution to artifacts. While the scientific process will ultimately prevail, the eventually can feel protracted when observed in real time. 3I Atlas, in contrast, is following a more accelerated trajectory, traversing the inner solar system. Peak observation opportunities are imminent. If NASA intends to release comprehensive data, it must do so soon. Once the object moves beyond the Sun's immediate vicinity, its activity subsides, and it begins its return journey into interstellar space. The window of opportunity will close. The available data will be limited to what was collected during this brief period, and future historians will evaluate NASA's stewardship of this crucial time frame. The concluding section will provide a forward-looking perspective on upcoming observational prospects and the enduring questions that remain unanswered. Part 15. Cliffhanger and Call to Observe. 3. IATLAS will reach perihelion, its closest point to the Sun, on September 11, 2025. As of this recording, this is less than 3 weeks away. During a comet's perihelion passage, its activity peaks. Outgassing intensifies, jets become more pronounced, and its brightness increases. Any unusual characteristics are most likely to be observable at this juncture. NASA is aware of this, as are all major observatories. The James Webb Space Telescope has scheduled observation time. The Hubble telescope, already engaged in observation, will continue its watch. Ground-based observatories across both hemispheres are coordinating observational campaigns. This is the pivotal moment when the most valuable data regarding this object will be acquired. However, a crucial question arises. Will this data be made accessible? Will NASA release it promptly? Or will it enter the aforementioned review queues? Will images be available in public archives within days? Or will the public face weeks or months of waiting while the data undergoes analysis? spacecraft considerations also come into play. The Parker Solar Probe, NASA's mission dedicated to studying the Sun, will be positioned in the inner solar system during 3I Atlas's perihelion passage. While not designed for comet observation, the probe is equipped with cameras. Should 3I Atlas pass sufficiently close to Parker's trajectory, its cameras could capture images from an Earth-independent perspective. Would NASA expedite the release of Parker data if it revealed something unusual? Or would data from such a high-value mission, with its complex instrumentation, be subjected to even more rigorous review than telescope observations? The European Space Agency's solar orbiter is also in proximity. This spacecraft, like Parker, was not specifically designed for comet observation, but possesses the capability to do so if the opportunity arises. If Solar Orbiter captures images, ESA's historical performance suggests a more rapid release of data compared to NASA. It is possible that European data may precede American data, mirroring the pattern observed in July. Congressional interest is escalating. The House Science Committee has been monitoring the situation. While no formal hearings have been scheduled, congressional staffers have been making inquiries. If the perihelion passage yields dramatic observations and NASA persists in delaying their release, congressional pressure is likely to intensify, potentially leading to hearings. NASA leadership might be called upon to testify regarding data release policies. There are also unconfirmed but persistent rumors suggesting that at least one major peer-reviewed journal is currently reviewing papers pertaining to 3I's Atlas. These papers are subject to embargo, meaning their findings cannot be publicly disclosed until their official publication. However, the very act of submitting research for peer review signifies that scientists consider their findings significant enough for dissemination. What do these findings actually reveal? We remain in the dark for now, but the unveiling will occur once the information embargo is lifted. Amateur astronomers are actively preparing observation initiatives. With even basic instruments, backyard telescopes are capable of tracking 3 Atlas and assessing its luminosity. While these citizen scientist observations may not possess the same level of detail as those from professional observatories, they will be made public without delay. There will be no lengthy review cycles, no organizational limitations, simply unadulterated observations shared across online forums and social media platforms. Should amateur observers detect any extraordinary phenomena that NASA has not yet publicly addressed, such a discrepancy would undoubtedly ignite speculative theories. Conversely, if these amateur observations reveal nothing out of the ordinary, it could lend credence to a natural explanation and alleviate pressure on NASA. Regardless of the outcome, the community of amateur astronomers is poised to play a crucial role in this unfolding narrative. The ultimate, pivotal question that warrants your continued attention arises if NASA's subsequent data dissemination appears unusually manipulated, perhaps with certain areas of images obscured or sections cropped, or if specific spectral bands are included while others are conspicuously absent. Furthermore, if the timing of these releases seems strategically planned to minimize impact rather than maximize scientific insight. Could these circumstances suggest something beyond mere procedural prudence? We are not advancing claims of a conspiracy, nor are we suggesting NASA is deliberately concealing information. However, we contend that the emerging patterns hold significance. If the delays persist, if the released information remains incomplete, And if the explanations continue to be ambiguous, then we are compelled to question whether organizational self-preservation has superseded the commitment to scientific openness. NASA cannot simultaneously maintain absolute control and reveal unvarnished truth. Should they opt for control, prioritizing their institutional reputation over comprehensive disclosure, they might achieve short-term protection, but risk losing public trust in the long run. If, however, they choose truth, making all information available, even that which is uncertain or presents challenges, they risk immediate disruption, but potentially safeguard their credibility for the future. This situation transcends the confines of a single comet. It speaks to how humanity grapples with the discovery of something profoundly unexpected. It probes the capacity of our institutions to adapt to paradigm shifts, and whether our governance structures can accommodate unforeseen anomalies. It questions whether transparency and authority can coexist when the stakes are so elevated. Therefore, consider this an invitation. Remain engaged. Pay close attention over the coming month. Observe what is disseminated and the timing of its release. Compare the official pronouncements with the findings of amateur astronomers. Note the discrepancies in information provided by different agencies. Pose your questions. Advocate for transparency, but do so with discernment, acknowledging the challenges NASA faces while still holding them accountable. The forthcoming update holds the potential to fundamentally alter our perception of extraterrestrial visitors. Alternatively, it might simply confirm that 3 Atlas is an unusually peculiar comet, exotic yet natural, intriguing but not world-altering. In either scenario, the process by which we arrive at that understanding is as vital as the conclusion itself. September 11th marks the perihelion passage, the apex of observational opportunity, the moment when 3 Atlas will unveil its secrets, whatever they may be. Following this, a decision point will arrive. Will NASA share their observations with us, or will they necessitate a waiting period while review processes unfold, allowing speculation to fill the void? You are witnessing a trial, not merely a test of astrophysical interpretation, but an examination of institutional resilience, governmental efficacy, and humanity's capacity to confront the unknown with both bravery and circumspection. This trial remains ongoing. Its outcome is yet undetermined. However, the very fact that this discourse is occurring is indicative of our current societal standing. We possess the technological capabilities to scrutinize the cosmos with unprecedented precision. Our scientific understanding allows us to identify deviations from established models. We have communication networks that can disseminate information globally in mere moments. Yet, we are also constrained by organizational limitations, political pressures, legal frameworks, and inherent human psychology. All these factors collectively complicate the straightforward act of reporting observed phenomena. 3 Atlas continues its trajectory, and time is of the essence. Whatever decisions NASA deems necessary, they must be made imminently. Whatever knowledge they possess, it must be shared before the celestial body recedes beyond the optimal range for observation. The countdown is underway. The world is attentive. And somewhere within an institution where data is scrutinized and decisions are deliberated, individuals are grappling with exceedingly difficult choices. What they choose not to reveal may well constitute the true narrative. But perhaps, just perhaps, in the weeks ahead, they will disclose everything. And then we will possess knowledge, not only of 3 Atlas's true nature, but also of our institution's capacity to manage truth when that truth is more extraordinary than anticipated. Maintain your curiosity, your skepticism, and your vigilance. The next chapter is poised to unfold, and it will illuminate as much about ourselves as it does about an interstellar visitor that selected this precise moment, this year, this cosmic alignment to traverse our solar system, challenging all our preconceived notions about the universe's workings and our own reactions to its surprises. The telescopic imagery is being captured this very instant. The data is being gathered. The analysis is in progress. And soon, very soon, we will ascertain whether NASA trusts us with the truth, or if their untenable predicament compels them to opt for silence over disclosure.